Hello friends, good afternoon and welcome to EduSat live lectures. Dear friends, today in networks and graphs we will be talking about applications and significance of graphs. To discuss this topic we have with us our subject expert Dr. Aditya Sinha. Dr. Sinha is Assistant Professor in Department of Computer Science in a very eminent university in NCR of Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Thank you very much. Okay. Hello everyone. The main purpose of this lecture is to get you introduced about the significance of graphs through different applicabilities of it. So the contents that we are going to cover is to introduce to the definition of graph, its mathematical background, okay, then going through some significance, its widespread applicability across domains. Of course, we'll talk about some very predominant properties of graphs, and we'll come across certain basic terminologies that are associated with graph theory. And then we'll try to understand how network is converged with the idea of how the graphical layout of the nodes and the connectivity are. So let's start with what is a graph actually. Mathematically speaking, it's basically a symbolic representation of pairwise relation of different objects. When we are saying objects, they are all discrete objects. So the type of pairwise relation that different objects shares with each other, maybe in symmetric or asymmetric fashion, is called a graph. Okay. Now this relation can be in form of a connectivity. Connectivity means that, say there are two objects A and B and they are connected to each other, then there will be a link or an edge between those two objects. Okay. Similarly, it can be interactivity, that whether it interacts or not, whether if two objects are not interacting, there won't be any edge connecting those two objects. Then also it can be, the relationship can be in form of a similar property. If two or more objects are sharing similar properties, then they will get connected, etc. Or it can be belongingness, whether it belongs to a particular property or belongs to a particular group or something, some community, then they will get connected. So there are different ways of how this pairwise relation can be defined according to the application. So in the figures we can see that there are some types are shown. The first is uniform tree structure. So it's like a fractal, it's a uniform fractal. It's starting from a root and getting into three child nodes. Each time the level is increased. It can be a non-uniform one as well, as we can see in the second figure, or it can happen like it's not at all a tree. It might be some regular or irregular or just a random graph. A cyclic structure is shown in figure 3. So when we are talking about graph, it is the simplest idea is about the distribution of nodes in depending upon how they are interacting or they are say their similar properties are, they are getting connected by some edge. Okay. So with this simplest conception, if we want to define it through symbols, that how the properties of the graph can, how we can see the vertex set and the edge set, the nodes that we are saying that they are nothing but they belong to the vertex set. Okay. So a very simple mathematical definition of a graph is there are two sections that we have here, the vertex set and the edge set. Vertex set is what? It is a collection of vertices. Say here we have n vertices, and edges, there are m edges. Edges can be also synonymously called the relations or links. Okay, so when we are talking about from the network perspective, we often call it links, and when we are modeling it, we call it edges, and when we are talking about some social relevance graphs or something like that, we call it as a relation. So all these are synonymous terms. Similarly, vertex is also synonymously can be represented as objects or nodes. Okay, so here we can see in equation 6 that we have 4 different properties that are exhibited mathematically. The first is that it belongs to the vertex set V. The first part of equation 6 is what? It's like vertex Vi and Vj should be belonging to the set V. That is, V is what? V is the vertex set of the graph. Okay, so it cannot happen that any other node outside the vertex set is getting connected. No, it should be all the nodes within the vertex set that are defined within the vertex set will get connected only. Okay, then also I is not equal to j. What is the interpretation of that? It means that there are no self loops. Self loops means that a node is not connected to itself. Okay, unless otherwise stated, a simple graph will not have any type of loops. Third one says that there are no multi-links. It means that if there is one edge between two objects, say A and B are linked with one link, they will be not linked over and over again, right? That is what there are no multi-links or multiple links. As we can see that it's EI and it's a operator which is used to find out the common elements between EI and EK. We can see that the intersection of EI and EK gives a null set. So there is no common element, and K is obviously not equal to I again. So all the edges that we have has to be distinct. Okay, and there is a two vertex connectivity. It means that an edge can at most connect only two vertices. Exactly, it has to connect two vertices. Okay, so if it's connecting a single vertex, then it becomes a loop, which is out of scope from the definition of simple graph. So we are only interested about the edges that are connecting exactly two vertices. Okay. Also, if this number increases, say it is getting connected to 3, 4 or even some L members, so it becomes a general graph which we will be talking about later. It is known as hypergraphs. Okay? So for the time being, we are only concerned with the simple graph definition. So this is the definition, the mathematical background of what a graph is. Now let's and try to understand the different significance associated with this type of graph. So this graph it can be used to present the different networked components in a very easy manner. Okay, like seeing the network components or verbally stating them that okay, this object or this station or whatever, some people is getting connected to some other people in some different community. So it's not a very like interpretive one. Okay, so if we have, instead of saying it verbally, if we are presenting a graph in front of a person that okay, let's say that this is the layout, then it will become more easy to comprehend the basic idea. Okay, so network components can be easily comprehended. What else? It can represent all forms of the information that is associated with the nodes or links that we'll see just now. And this information can be represented through those the vertex and the edge set. Okay. Now applicability, if you're talking about the applicability of graph, it's immense. It's spread over cross-disciplinary streams, be it computer science or social sciences or mathematics or statistics. Everywhere we can find out the relevance of graph. And it also facilitates the analysis of the links, that is the edges, to give a good interpretation of so many different results, like identifying the nature of flow of information. Obviously how the information is flowing or not, whether it is flowing at all or not. So this can be exhibited with a graph. Also revealing pattern for diffusion of data. Say for example, in a social network, if a node in the entire graph is sending some message or it's tweeting something, so to who else this message is going, whether it is getting flooded in the network, that is all the people connected in that same social network are getting the message of that person, or few are getting, or just one of the person is being sent to. Okay, so this type of how the data is being spread, the diffusion, this also can be revealed with the help of graph. Then of course discovery of shortest paths. When we are talking about graph, through links we can count the number of links between a particular node to another node and find out then how many number of links we are traversing it. So less number of links traversed, it means that it's a shortest path. So there are so many algorithms to find out the shortest path, shortest possible time, shortest delay incurred to get the message delivered from one person to another in the network. What else? It can be planning of optimal schedules in offices, in management. What happens, people have to achieve tough deadlines. It has to these type of processes, they can be laid out in a graph, and a particular schedule can be finalized by seeing how the graph has been constructed out of the informations that are given. Okay. What else? The highlighting of central nodes, obviously, because in a network, in a closely connected network, what happens that some of the nodes are sharing very high importance in the network, in the closed community. Okay, so how to find out those nodes? Maybe it can happen that the nodes are having, say, good number of close neighborhood. Okay, the size of the neighborhood is very compact. It means that he is very popular in its close community. So in that manner, if we are seeing maybe he's central, or the reachability of the person in the connected community is high, very high. So we can say that it's central in terms of reachability, in terms of its neighborhood size. So there are different centralized parameters to find out the centrality of that particular node. So they are there, and there are strategic networks as well. What happens in strategic network is the costs and benefits can be very finely analyzed, and with the help of the critical analysis done on the cost benefit basis, so many important decisions in the management or in the company can be done. And graphs are what they need visualization. Okay, so it's not just pen and paper work, because in most of the real-time networks, be it social network, Twitter networks, even the transportation networks, we'll see a large number of list of networks just now. So all these networks are what they're very vast. They have so many number of nodes. Some network may be sparse connected, or it may be densely connected. So it's not always possible to just draw it down on a pen and paper. Okay, so we need some good visualization tool as well, not just for mining the data, not just for finding out the information, gathering information, etc. We also need to visualize it. So there are so many good tools available online. They are open source tools. You can just go and download it from the sites, and they can be used for finding out all these types of complex interpretations, everything. Like Gephi is one of them. Pagic is also a good analyzer. So there are a large number of softwares available online. Now let's see the types of network. Okay, so this is obviously not a very exhaustive list, but it traverses like most of the important networks that are available. Okay, so the first one is technological network. In technological network, what happens if we are trying to see it from the viewpoint of nodes and edges and some of its instances, then nodes will be the power stations, or places, right? Because technological networks can be the power grid networks or the transport networks, that is which roads, which places are getting connected through wires, I mean through lanes and etc., or there are some power stations situated, then the power stations are being connected through wires, which areas power stations are connected, which are not. Okay, and places can be obviously connected through rails, it can be through airways, etc. So if we check this technological network through an eagle's eye view, we'll find that it's nothing but it's a graph, it's a networked graph, and where the nodes are the places itself. Okay. Next is communication graph. We all are very much into communication, right? And in some instances could be internet itself or telephone network, etc. So here also the people who are having the handsets or have taken SIM, registered for SIM, they are all a part of the vertex set. So it can be the mobile phones, so the users who have registered, because these days users are having so many number of SIMs altogether, okay, maybe having 2 or 3 numbers registered. So that way the users, the laptops through which we are doing the internet, okay. And what will be the edges? It will be the link, the coverage getting overlapped with each other of 2 devices. It means that there is a link, or it can be a coverage. And obviously we have endorsement network. Endorsement network is what mainly the researchers are using this type of network for citation, etc., that they have published some work and someone else is citing their work. It means that whenever some other person is citing the work, then there is a connectivity between the person who has cited and between the person whose work is being cited. Okay, so here the nodes will be what? The nodes will be the web pages. So it can be the research articles, papers, etc. And most important instance are the citation graphs, the patent networks, etc. Then we have the information graph. Now, how information graph is different than the endorsement graph? As we can see that in endorsement graph, the person gets endorsed of their research that they have done. Okay, so it's a proof that their research is very good, very valid across the web and have some significance of work in it, etc. And that's why they are being cited, they are being referred. And what happens in the information graph is like it's a bank of information. Some web pages are connected to some other web pages through hyperlinks. We are all aware of the hyperlinks. So in this way the references are working through text hyperlinks or through image hyperlinks, etc. So the referencing that is being done in the information graph is a little different than the referencing that is being done in the endorsement network, because whenever there is a reference in endorsement network, it means that the person who has given the article, who has published the article, are getting some credit. Okay. So also again we have metabolic networks. Metabolic networks, in such networks the nodes will be the cells and the neurons, and if the cells are a part of some metabolic processes, then these metabolic processes become the edge, and over and all we can see that brain networks and different neural networks, as we have these days artificial networks also, so it's better to say the biological neural networks. So these are all part of metabolic networks. Then ecological networks are there, the food webs, as we all know, the living beings will become the nodes, and who eats whom, like it's a type of consumption, the dependency will become the link. Okay. Now let's try to see more examples. This way it will be clearer in your mind that what is the interpretation of the vertex set or nodes and the relations or the link set. Okay. So given any application, you will be easily finding out that okay, yes, if this is the application, then these will be my node set and the relations will be like this, and then let's do the mapping and all. Okay, so for that purpose, let's study some more networks. The logistical network. What happens in logistical network is this mostly happens in management or production type companies. Whenever there are 2 departments are connected, that is a output from one department is getting as input to other department, then we can say that these departments are connected and we have an edge in it, right? So the edges can be the process control, a module dependency, some production flow line, okay, and packaging, warehousing. These are all the applications of logistical networks. And these networks, believe me, they are very vast because they are spread across nations. And we are studying computers, so computer network is also there. Computer networks, what happens, nodes can be the computers, the big end servers, or the workstations, base stations, etc. And again, if they are connected through wired topology or wireless coverage, then these will act as the edges. Okay. It can be the sensor network, ad hoc network as examples, even the wired old backbone networks, etc. can be some of the instances. Then of course social network, we are all doing these days social networking, and social networking, as it's needless to say that people and different communities, they act as nodes, and whether they are communicating or say they are frequently communicating or not, what type of communication is being going on, the nature of the communication, etc. So these can be acting as the edges, and examples, it's like Facebook, WhatsApp, Flickr, etc. Then two very important examples that comes into my mind is the taste graph and interest graph. Okay, taste graph and interest graph, they both have in the node set as people. People are doing, say, different types of recommendation graphs like Hunch, etc. Or they are doing tweeting, or say they are into Quora or Instagram. So this type of applications are there, and the edges are, when we are talking about the taste graph, is on the basis of taste similarity, the objects are getting connected, or if they share a common interest, they are getting connected, and we call it an interest graph. So, but this taste and interest, they are almost very similar to us, right? So how to know that what is the basic difference in it? So let's study, just have a little look on it. In taste graph, what happens, we try to be of corporate relevance, and when we are on the interest graph, we are trying to focus on the personal interest. Okay, let's see how it is. Test graph are what they are built over massive data from the accounts of different individuals, while the interest graphs are constructed on one or more user profiles. It can be obviously done on a single individual user profile to see whether what type of interest that person shares, maybe in what type of movies he likes, or say the games, football, cricket. So it's a mapping of just a one person and what type of interest it will have depending upon the attributes that are there of Facebook or Twitter, or etc. Okay. But in taste graph, what happens, it cannot be done for a single person, then it will be irrelevant. Okay. So as interest graph is concerned, it can be one or two or more. Often they are over very few socially connected nodes. But in taste graph, what happens, it can be those people getting connected or getting recommended, those who were not socially connected before. This mostly happens in corporate, because two persons, they are not knowing each other, but they might be working on the same project, or they might be sharing some community interest, etc. So likewise, they can be recommended to get connected. So it's all about recommendation on the corporate level, right? And in interest graph, what happens, they are built only across those people who are already socially connected. And taste graphs are used to introduce to new customers, as we are checking out the scope from the corporate viewpoint. So obviously new customers can get introduced, there's chances of new interactions, new opportunities, etc. And in interest graph, they are simply analysis of likes and dislikes. If 2% they have liked a certain tweeted message or something, some image, etc., repeatedly, then they have a stronger connection and it gets visible in the interest graph. Okay, so it's nothing but a visual interpretation of the interest that people share, or people belonging to a very close community they share. Okay, so this is what a taste interest graph. And by now I think it's very much clear in your mind that how an application can get modeled using graphs. And one more thing that should be clearer by now, that there is a difference between graph and networks. As networks, we know they are often for communication, more importantly computer networks, wired networks and wireless networks. They are all for communication, the exchange of messages electronically, right? When we are talking about networks, it means that we are talking about some real-time networks, some electronic computer networks, or it can be some telephone networks, or any network that is already on the real world, it's working, okay, and we are trying to analyze them. And when we are talking about graphs, graphs means that those are not yet there, or there might be some more research that can be done to enhance their properties. So when we are talking about the modeling part, it's normally the graph is being used, and when we are talking about the real instances, we are mostly using the network term, right? But they are almost like synonymous, we can say, from so many viewpoints. So let's move ahead. Let's study the properties of graph. The first is node scalability. From the point of view of how many nodes are being there, it may be any domain. So we have came across so many domains by now: technological network, logistic network, wired wireless networks, and so many networks. So I'm not getting attached to a particular application. So it can be people, or it can be some objects. Whatever it is, it will be discrete. Okay. So these discrete items or discrete objects, how many of them are there? So this is what the scalability is. So it can be highly dense, or it can be a sparse collection of nodes. Now once the nodes are there, once we have the vertices there, then how they are connected to each other, whether they are closely connected or they are having a weak connection, that is, less number of connections are there. Okay, so this will be your link distribution: more number of links or less number of links. So in the diagram you can see that the first diagram, it shows a sparse nodes with strong connections. The number of nodes are few, but whatever number of nodes are there, they are strongly connected. More number of links can be visible. Okay, and in the second figure we can see that apparently the links are very less, but the number of nodes are more. But obviously, if we are concerned about, say, Facebook type application, so these number of nodes will be less. Then of course we have in the third figure the dense nodes with strong connections. As we can see, it's full of network, and so many nodes are there. Some of the nodes can be highly important, so their size can get increased and all. Okay, so now we move to some more properties of the graph, internal properties and external properties of the graphs. In the internal properties, what happens, there can be the World Wide Web. If you are talking about, then the nodes can be the creator page or the length, the creation date or time. All these can be the nodes, and links can be what, the repeated, whether they are repeated more than once or not. They are active links or passive links, etc. Similarly, there can be Twitter. If we are talking about Twitter, then what type of nodes and links are there, etc. Okay, and external informations can be point-wise, pair-wise, or it can be list-wise. Let's discuss more on this after a short break. Thank you. welcome back. We were talking about the external information that can be stored on graphs. It can be pointwise. Pointwise means that some object can be more important, like like if you are talking about the mails that we receive on Gmail, etc. What happens? There is a section called spam. They are less important mails, so they are put into spam. Okay. Some mails that you don't find it important, you put it into trash. So say some mails, M1 is a trash, M2 is a spam, M3 is a very important mail. If it's a very important mail, we often mark it as star, etc. Okay, so it's all about importance, and the importance is not interrelated or interdependent, that the mail X is more important than mail Y, etc. It's a standalone thing, whether that mail is very important to us, it's not important, or just let trash it, like that. Okay. So these are all what they are point-wise description. It can be pairwise also when the interdependency comes, when we are comparing, like from the say some viewpoint that this is more important than some other object. So it can be a pairwise comparison. And when this pairwise comparison spans across more number of discrete objects, it becomes a listwise comparison. And when we are talking about a list, it means that we are not comparing it, we are actually relatively, we are ranking it. We are listing, the list is there and we are ranking it, okay, the first one is more important, then the second one should come, and likewise. Okay, so we are listing the importance, listing the objects according to their importance in any order, ascending or descending order. Okay, so these are the three important type of external information that can be stored on graph. Now let's study about some of the basic terminologies we often might come across when we move to more advanced form of lectures. Okay, so the first is undirected graph. In the beginning, it was told that the relation, the pairwise relation is it can be symmetric or it can be asymmetric. Okay, so undirectedness, when we are concerned about this, it means that it is a symmetric pairwise relation. It means that, as in the figure type A, if we are saying that A is connected to B, it will mean that B is also connected to A. It's not needed to specifically or explicitly specify it, right? So the major concern over here is connectivity, because all the links over here are bidirectional. A is connected to B, B is connected to A. So it's a bidirectional link. Okay. So the directivity, of course, it's not important here. And when we are showing it, when we are laying it down with the help of a adjacency matrix, we can also see the entries that we have the list of vertices A to F in both rows and columns, and logic is if say A is connected to B, then there will be a 1. If A is not connected to B, then the entry will be 0. It's just the show of whether the connection exists between a particular pair of node or not. In that manner, this entire matrix is defined, and one important thing that we can see over here is all the diagonal elements are 0. The meaning is that none of the nodes are connected to itself. As in the beginning, we told that it was told that unless and otherwise stated, the simple graphs will not have self loops. Okay, so no node is connected to itself. There is no interpretation for as of now. Okay, so these entries will be 0, and is over the diagonal elements and under the diagonal elements, we can see that the entries are all symmetric. Why? Because the relations are symmetric. For the same reason, the entries also we find it symmetric. And what type of application interpretation that we get from the undirected graph? It can be simply the existence of communication. The links will exist only when there is a existence of communication. Two persons are communicating, then there will be a link, otherwise there will be not. And what else? The occurrence of events. Events occurred, there say two places that are connected, some event occurred, there will be a link, the graph will be visible to the person that okay, some events has been there has been some event. We are not concerned about who triggered the event, right? So this is just the occurrence of events. Else, what else? The continuation of services. Say some station A is providing some service to some mobile devices or something, and then all those devices are getting connected to that particular station. We are not concerned about who is providing the service to whom. It's just that the service is being provided. Okay, this is the undirected nature of a graph. Now let's move ahead. Now comes the directed graph. Here the directivity is of main concern. Again, unless otherwise specified, the outlinks are the most important ones that we are concerned about, especially when we are designing the adjacency matrix. Now here again, to notice that the diagonal elements are all 0, but now the elements over and above the diagonal are not similar, they are different, which means that now the entries are asymmetric. Even in the graphs you can see that in type A, now if we are saying that A is connected to B, it will become a false statement. Okay? Even in type B, it's visible that only B is connected to A, not A is connected to B, as the direction shows. And if we want to display some bidirectional link here, okay, so what we can do, as you can see the BC edge in type B graph, it's just an edge, it's there, it seems that it's a undirected edge, but it means that B is also connected to C and C is also connected to A. So if you put two arrows simultaneously, it will also mean the same. Okay, and the interpretation will be here as we were talking about communication in the previous undirected version. In the directed version, it will be the direction of the transmission, from whom the transmission of some message or packets are being initiated and where it will be moving to. So now the direction of transmission is important because directivity has come into focus. Then triggering of events, not just the occurrence of events. Now we are interested to know that which object has triggered or what type of event has been triggered by what event earlier has already taken place. Okay, so the triggering of event is now important. Then imparting of services, not just continuation of services or existence of services. It's like who provided the services to whom. Okay, so this is the interpretation of those graphs that are being designed with the help of directed links. Okay, now let's move ahead more. Now let's understand what a degree is. Now, degree is what? Degree is mainly associated with a vertex. So in the graph you can see that the node B is having 3 links or 3 edges. So we can say that the degree of node is 3. Similarly, if we are talking about the directed links, the directed graph, in it what happens? If we are interested to know about the out degree of F, then it will be how many nodes that are going out from F. So it is number is 2 because it's going towards A and it's going towards the node E, as you can see in the graph. So this is what the out degree will become 2 in case of F, and in degree there is only one link coming towards it, so it is 1. So in directed case the degree are of 2 types, out degree and in degree. In case of undirectedness, it is just how many links or how many edges are incident on that particular vertex. So it's simply the measure of total number of edges incident on the vertex Vi. This is a mathematical statement if we are interested to define. Then there are adjacent nodes and adjacent edges. Now what are adjacent nodes? They are simply those nodes that are sharing the same edge. Okay, say for example node B and C would be adjacent to each other because they are sharing the common edge BC. Similarly, 2 edges will be called adjacent if they are having a node in common. For example, B is the edge BC is adjacent to the edge AB because they AB and BC, they are both having only one vertex in common, that is B. So, this edges will become adjacent to each other. Okay. So, this is all about degree, how the nodes or what type of nodes or edges are called adjacent to each other, and what is the meaning of incidence. Incidence means that the links that are lying on a particular node. Okay, so that is incidence. Then come to path. Path is what? Before knowing path, it's important to know what a walk is, because walk is a more general term that is used, and it is often referred to a type of traversal of nodes in which the nodes that are coming in the walk, it can come a number of times. It's not that they are occurring just once. Okay, so it's like someone is taking a stroll and might be passing the same say street over and over again. Okay, as in the example, the first figure, we can see that node A and node B, they are getting traversed twice whenever whenever a walk is concerned. And what is a path? That type of walk will become a path where each node is being traversed not more than once. Okay, so walk also is there is an example over here, as we can see, starting from some node and going to another node in the same network, and we are traversing few nodes, but these nodes are not being revisited again. So if we are revisiting any node, it becomes a walk, otherwise it is a path. Then cycle. Cycle is a path in which the starting vertex and the ending vertex are same. Okay, so it's a path in which both the start and end point are going to be the same vertex, and a graph that contains at least one cycle, we call it a cyclic graph. As cyclic graph will be that type of graph in which there is no scope of having any cycles across its nodes. And tree, of course, is what? It's a acyclic graph in which if any edge is added to it, it will result into a cycle. As the figure, it's shown a rooted tree is there with one root and two branches, main branches, and of course there are so many leaf nodes in violet. So what happens here, if there is one edge, if we put anywhere into this graph, it will result into a cycle. Okay. So this is what about all about a walk, path, cycle and tree, because they you will see in lectures ahead that these terms, they have a certain significance. Then we have subgraph. A subgraph is what? A subgraph is normally concerned with original graph, as the first figure is showing the original graph. According to this graph, we have A to F vertices. So the list of vertex will be like A, B, C till F, and the number of edges we have, they all fall into the edges list. Now subgraph will be some graph that is denoted by H, such that it will have a different vertex set and a different edge set, but these sets will be a subset of the vertex and the edge set that the main graph is having, that the original graph is having. Okay. So it's just that we have been given a original graph and we have to construct a subgraph of that original graph, then we will only pick up some of the edges and some of the nodes, and whatever graph we design, it will become a subgraph. Okay. Then we have induced subgraph. There are different types of subgraph. So one of it is induced subgraph. Induced subgraph denoted by I, and it is shown in figure 3, that it is constructed with a vertex set that is of course a subset of the main graph vertex set. It can be any number of vertex, 1, 2 or any number of vertex, but the main concern is about the edge set. We can see here that only those edges can be there in the induced subgraph that are induced by the vertex set that is being chosen. Okay. In the example, let's see, it will be more clearer. In the third graph, the third figure, it's the induced subgraph BCG. Okay. So, if we are, say for example, before constructing the edges, before selecting the edges, we have taken all the vertices. The three, we are concerned about the three vertex B, C and G. We have put the points B, C, G, and now we are adding the edges. Only those edges will be added in induced graph whose both the endpoints is in the vertices that are in the already chosen vertex set, that is V cap. Okay. And see, there is a difference between the induced subgraph example and the subgraph example. In the subgraph example, we are having D, E, B, F, right. But in this section, if D, F is another edge, the diagonal one, if that edge is was there in the subgraph, then this subgraph would become an induced subgraph. Okay, but since that DF edge is not there, so we are not concerning, we are not taking it into consideration of a induced subgraph, rather it is a normal subgraph. Okay. Then we have clique. Clique is what? It is constructed out of, again, sum of a few vertices, so it is that same old V cap, and the edge set can be a little bit different. Let us see. Clique is what? It is a complete subgraph of the original graph. Okay. So, the clique example that we have just taken, it is also the induced subgraph, it is also a clique. Why? Because if we are checking out this graph B, C, G, there cannot be more edges into this subgraph that can be added, right. It's complete. So, that the subgraph that is complete in every sense and is induced by a certain number of vertices, here the vertex list will be B, C and G. So, that type of complete subgraph will be called a clique. Then of course, we have a spanning subgraph. Spanning subgraph is what? It's also known as a spanning tree as well, and here the subgraph should include, the constraint is that it should include all the vertices, exactly all the vertices that are there in the main graph set. All those vertices has to be there, but yes, there is a choice on us to take which edges we want. Okay, so there need not be all the edges taken, but the vertex has to be covered all. You are covering all the vertex of the original graph. Okay, so most of the times they are known as the spanning tree, because it's spanning across all the nodes of the graph. Okay, so given a graph, there can be different spanning trees generated out of it, and this type of spanning tree is having a very relevance when we are talking about any type of network in it, because given a network, an important concern is how to traverse in a minimum time or minimum weight associated or whatever, we will see it later. But let us come across some of the applications of a spanning tree. So, the first is designing physical networks. These networks can be telephone network or electrical networks, TV cables, etc. So, for that we are concerned about, say for example, TV cable has to be laid down. The minimum length of cable required, this will be given by the spanning tree, because spanning tree is traversing all the edges, that is all the places, all the homes in which TV connection has to be imparted. So, we are traversing all those homes, but we are also concerned about minimum cable that is required. So, the spanning is important, and when minimum length is also important, it becomes a minimum spanning tree. Okay. Then of course, we have a cluster analysis. In cluster analysis, spanning tree is having a great relevance. We want to find out clusters, which of the nodes are closely connected, which are not, etc. This can be done using the spanning tree. If you want to traverse all the nodes, then what are the different paths we have, etc. Then some indirect applications and approximate solutions are also there, where spanning tree is greatly brought into use. Maybe the traveling salesman problem, when we are mostly talking about routing problems in a network, the traveling salesman problem is there, Steiner tree, etc. This type of things are there. Indirect applications would be like describing the arrangement of nodes, as already told that given a particular original graph we have, we can generate different types of spanning tree out of it, right? It's just that the nodes, all the nodes has to be there. Second, it can be the modeling of the nodal connections, how the node are interacting with each other. If you want to show those, it can be easily done with the spanning tree, because the interaction is a thing that is very dynamic with respect to, say, changing community or changing time, etc. And we know that the spanning trees, there are so many spanning trees associated with a particular graph. So just change the spanning tree and we are able to show a different type of interactivity across the nodes. Now let's talk about the components. Components are what? They are maximal connected subgraph. Now let's get it clear, more clear with the examples. In the first figure we can see that there are two components. Actually it is only one graph, but the node that is circled, it is encircled, just it's isolated, it's not connected to the main graph, but it is there as a part of the graph. So we call it as a separate component. So C, the number of components in this case will be 2. But say we are adding some directivity, some direction to the same first graph, we get a second graph. In this what happens? We can see that once information reaches to the point A and B, or initially say some information are there in the point A and B, there is no way that the information will get propagated to the rest of the network. Okay. So why? Because the direction is towards them, there is no outlink from A and B. So in that case what happens? There are 4 components. Okay, the node A and B, they become separate out, they just separate out, and then rest of the components that we were already having. So with the direction of links, the components, the number of components tend to change. Okay, and obviously an isolated node is what? It's a node with degree 0. That type of node is inherently it is a part of the component. And defining a subgraph will be in this manner, that all the vertices that are reachable from one node to another through a path. That is there has to be a path, a proper connectivity that be at any node you can reach to any other node in the network. So if there is a connectedness in a subgraph of the same graph, then we could call it a component. Okay, as in the first graph we can see that there are 2 components. One more thing to note, that there is one component of the first graph having 4 nodes. So we often call it a giant component or GC. There is a theorem associated with a subgraph that is quite evidently used. It says that the graph with n vertices and say m edges will have n minus m components. Okay, and this is a at least factor, at least it will have these many components. Now how it's possible? Because whenever we are talking about say n graph means what? N vertex graph means that they are not connected with any edge with each other. Okay, so they are all disconnected nodes. So at large we can say that n vertex graph is having n components. Okay, and whenever we are adding one edge, what we are doing? We are reducing this number of component by at most 1. Okay, so in this manner, if we go on adding edges till m edges are being added, so evidently the number of components will be at least n minus m. Even we can see it from the example, small example here in figure A, showing the undirected case. Initially all these nodes from A to F nodes, they are all unattached, they are not connected with each other, and one by one we are adding the edges, like AB edge is added. Okay, so what happens? The number of components is also getting increased it's getting decreased, and the number of edges are getting increased, right? So as the number of edges get increased, the number of components tend to decrease, and they decrease by the factor n minus m. If we are taking up the undirected case, then what happens? We are getting, see in this example, in the second one, in the figure B, we are having two components, because the edge EB and EC, they are moving outwards from the vertex E. So if we are in the first subgraph, that is comprising of the vertices A, B, C and D, there is no way that we can move, we can traverse to the second part of the graph. So though they are directed, they are connected in a directed manner, but still there will be two components. Now the connected graph. Connected graph, from the undirected point of view, it's called a connected only when there exists at least one path between any pair of nodes, and that is what? That is reachability, obviously, from one node to any other node in the network. And if we are concerned, if we want to define it in terms of the component that just we have studied, it means that if there is a single connected component, we call it a connected graph. As in the figure, the connected graph, as we can see that all the nodes are connected. Initially, if a person is in any of the vertices, it can reach to any other vertex by traversing the links. In the directed case, there will be existence of the directed paths. So wherever the directivity goes, the flow of information or the flow of messages, etc., can be traversed in that direction only. A graph is called a strongly connected graph if there is a presence of a strong connection between them, right? That is, each and every node in the graph are directly connected. Directly connected means that they are connected by one hop distance. Okay, so in the figure we can see that A, B, C, they are all connected to each other. We cannot have more edges, so it becomes a strongly connected graph. Okay, so in this lecture we have came across all these terms, etc., and the significance. In the next lecture, in the preceding lectures, we will all talk about more and more on the terminologies associated with, so as to understand the fundamentals of graph. Thank you.
On that note, I would like to thank ma'am for this very enriching discussion, and thank you, dear friends, for watching our show. Stay tuned and keep watching. Thank you.